Hello everyone, my name is Dr. Devabroto Samanto. I'm an assistant professor of DNC College of West Bengal. This is a short-term course which is going to be interactive in blended mode, and the course title is Substitution Reaction. The objective of the course is to actively engage learners throughout the video lectures by interactive methods in blended mode of teaching, and the course is using a 4-quadrant approach, that is e-tutorial, e-content, discussion forum, as well as assessment. The course outline is following. There will be 4 lectures. The first lecture will be dealing with SN2 reaction, and the second one will deal with SN1 reaction. Third lecture is SNI reaction, that is SN internal, and the fourth one is about SNNGP, that means substitution nucleophilic neighboring group participation. In this tutorial, this is the lecture 1 of this course, we are going to learn about SN2 reaction, that is substitution nucleophilic of second order. Now we have to understand that what is substitution reaction. Nucleophilic substitution reaction occurs when the substrate is attached by a nucleophile and the leaving group differs. The reaction takes place at the saturated carbon atom. Saturated carbon atom means when the carbon is sp3 hybridized, that means it has 4 bonds connected with it. Nucleophilic substitution reactions which follow the second order kinetics are known as SN2 reaction. The rate of second order reaction depends upon the concentration of both, that means the concentration of substrate and the concentration of reagent. The term SN2 stands for bimolecular nucleophilic substitution. These reactions are completed in a single step by the displacement of leaving group by a nucleophile and no intermediate is formed. This is very important. SN2 reactions always goes through a possible transition state. During transition state, the bond to the nucleophile forms at the same time that the bond to the leaving group breaks, because at no time can the carbon have more than 8 electrons in its outer shell. Therefore, the nucleophile is required to approach from the backside, and configuration at carbon is inverted. Other way around, we can say, if nucleophile attacks the substrate carbon 180 degree away from the leaving group, which is regarded as rear side or back side attack, resulting the inversion of configuration. The mechanism of these reactions may be represented as here. During the formation of transition state, the substrate carbon loses the sp3 hybridized state and attains the sp2 hybridized state with one unhybridized p orbital in a perpendicular direction to the trigonal plane containing the carbon with the non-reacting groups. One lobe of this p orbital overlaps with the leaving groups, and its opposite lobe may overlap with the nucleophile. Therefore, the nucleophile can undergo rear side attack in these reactions. In the transition state, the carbon and non-reacting groups are almost coplanar. If the leaving group and nucleophile are identical, then the geometry of the transition state should be perfectly planar. The energy required to break the CX bond had been supplied by the simultaneous formation of CY bond. SN2 products are stereospecific because stereoisomeric reactants give stereochemically different products. They are also stereoselective because they form exclusively or predominantly only one of a possible pair of enantiomers or one of the possible diastereomers. This is one example of SN2 reaction. The reaction between methyl bromide and a strong base, that is hydroxide ion generated from sodium hydroxide possibly. The rate determining step involves both CH3Br, that means methyl bromide, and hydroxide. The reaction between two reactants resulting in the direct displacement of bromide ion and hydroxide group occurs in such a way that a new carbon OH bond is being formed, while the old CBr bond starts breaking. Thus, the bond formation and bond breaking occurs simultaneously. Hence, the reaction is one-step reaction without any intermediate. While the reaction is taking place, the energetic hydroxide ion approaches the methyl bromide from the opposite side of the bromine to avoid repulsion between hydroxide and bromide ions. In the reaction medium, the hydroxide ion approaches the electron deficient carbon atom, following which the CBr bond starts stretching. At one stage, both bromine and hydroxide are partially bonded to the central carbon atom, which is known as the transition state. In the transition state, partial negative charge on OH ion is transferred to the bromine through the central carbon atom. At last, the approaching OH ion, that means hydroxide ion, results in the formation of the complete COH bond formation, and in this process, bromine ion departs. In the transition stage, a total of 5 atoms or groups are attached to the central carbon atom. As we move in the series from methyl bromide to tertiary butyl chloride, that is from 1 degree to 3 degree, a decrease in the nucleophilic attack was found at the carbon bearing the bromine atom due to steric hindrance of the attached groups or atoms. Or we can say that the nucleophile does not get any space to attack to the carbon atom. The flash eye effect along the series makes the carbon bearing the bromine progressively less positively charged and consequently less readily attacked by the nucleophile.